A maze consists of n rooms numbered from 1 to n, and some rooms are connected by corridors. You are given a 2D integer array, corridors, where the corridor at the ith index is a tuple of a room number 1, room number 2, and that shows that there is a corridor connecting both rooms, allowing a person in the maze to go from room 1 to room 2 and vice versa. The designer of the maze wants to know how confusing the maze is. The confusion score is the number of different cycles of length 3. For example, moving from room 1 to 2 to 3 back to 1 is a cycle of length 3. But 1, 2, 3 to 4 and 1, 2, 3, 2, 1 are not. Two cycles are considered to be different if one or more of the rooms visited in the first cycle is or are not in the second cycle. Okay? Return the confusion score of the maze. So how many cycles of 3 are there in the maze? And so in this case, we get these corridors, and we visualize them here. And from this, we can see that 1, 2, 4, 1 is a cycle of 3 rooms, and 1, 4, 3, 2 is another cycle of 3 rooms, and that's all we've got in this case. Here, there's no cycle of 3 rooms, so return 0, and that's all there is to this problem. Now for the solution, we use a graph algorithm because we're using graphs to solve things these days. And now, so we are going to initialize a map for our adjacency matrix called neighbors, containing all rooms as keys and their neighboring rooms as corresponding values. And in the code, we do that over here. We just create a neighbors map. As you can see, since the corridor at the ith index represents a corridor showing the two rooms are connected, we update the adjacency matrix like so. Okay. So this is where we update the adjacency matrix. We keep track of the cycles. That's what we're going to return. This is the value we're going to return. So we're going to loop through every single corridor, and the corridors come in this format, this tuple format of room 1 and room 2, that show that they're connected by a corridor. Now, when we add, this is when we add the rooms to the adjacency list, and so you get something that looks like this. Okay. Imagine this is our adjacency list. So for the keys are the rooms, and then the values are a set of all the rooms that are connected to that particular key. And that all that logic happens here. So basically you're checking, is it in the map already? If it isn't, then initialize it. This just initializes that particular key for the map. Then it gets that same thing we just initialized and adds whatever room we're evaluating to it. Then of course it's reciprocal, right? If 1 is connected to 2, 2 is connected to 1. And so we have to do the exact same thing, but this time for room 2. And we do the exact same thing there. Now, the next part is where the good stuff happens. We get the intersection of both rooms at each turn. And whenever there's an intersection, we have a cycle, 3-room cycle, which counts as a single cycle. And so that logic is over here. So for every iteration within our list of corridors, we set the intersection size to 0. Then we get that neighbor, get that room, get the neighbors for room 1, get room 2's neighbors. And now for every intersection, this is how we check the intersection. We're looping through all the neighbors of set 1 and checking if any of them appear in the list of neighbors in set 2, in room 2. And then whenever we see any intersection, that's a cycle count of 1. So we can just bump it up. All right. And so that keeps it simple. I can imagine if the cycle count had to be 4, this problem gets more complicated. And that's a way to modify this question if you're trying to be creative and see if someone really gets the concept. But yeah, that's that about that really. Once you do that, you're gonna then append it to the number of total cycles you see. And since it's a set, everything is going to be distinct. There's not going to be any duplicates in there. And return the cycles. C'est fini. That's all there is to it. This diagram tries to walk through it, but they use fancy words like cardinality, right? Which is basically just the number of items in the intersection. that I wasn't really feeling. So this is like kind of a visualization of what happens that I don't know. This is one of their weaker visualizations, to be honest. So I'm not going to sweat it too much, quite frankly. Let's look at the time complexity. So it's n by m, where n is the number of rooms, m represents the number of corridors, which kind of you can intuit. And then the space complexity is n squared. Because why is it n squared? Okay, it's n squared because in the worst case, every room is connected to every other room, I would say. So your every single set is going to contain every single list room. So that's going to like double up very quickly because you have the keys, which are individual rooms, and then every single one has, it's full connected to every single one. So that does make sense. And that's all there is to this problem. See you in the next one. Like, comment, subscribe, upvote, share. Thank you so much. Cheers.